Guys, how are you? Today we are going to talk about electric generators, a part of our turbine specialist package. And I think the turbine specialist is important. Know the electrical generators part well. If the student doesn't have this facility and electricity, then now he will have it. We will explain to you all the basics that we have most important to be able to follow up. And the optimization of turbines, always involving the electrical generators. We know that many turbines, many steam turbines, they deliver power to electric generators, and that's an important part of our course. So, what are we seeing in our module? Describe the operating principles of electric generators. We have most of the generators there that we use in the processes are synchronous generators. I will explain what a synchronous generator is. As I said, the purpose of this module is leveling and basic concepts of electricity for technicians, engineers, not electricians. So if you are a mechanical technician or a mechanic technician, chemistry, even the engineer, chemist or mechanical engineer and does not have, we know that there is not much familiarity, electrical systems with these disciplines. But here we are going to enter into a discussion. No, not in the depth that an electrical engineer or a technician. He has two electrical systems. But we will try to level all the concepts that are necessary so we can monitor an electrical machine. It is defined by the rotation that we apply to the generator. So the rotation we have here is an important variable. In other words, the more rotation there is in the generator, the higher the frequency will be. Another important piece of information is the number of turns that we have in our generator, and this number of turns is called poles. So in the case of our generator here, it is a simple generator. It has two poles, one pole and one pole above and one pole below. So, look, we determine each set of coils. People call of pole. The example here is that the generator has two poles. How do we define it then? The relationship between the rotation which is given in revolutions per minute in our unit at revolutions per minute and the generator frequency. It doesn't hurt to remember again what the composition is like. So of this electrical generation, of this sinusoid again, I have here the sinusoid that will be produced by the generator. I go to amplitude and I will have the period here, that is the time a cycle has been established. As we are talking about a cycle here, this one, in our case, this period will be 0.16 seconds, that is, in our current 60 Hz electrical current every cycle, we will have 0.16 seconds. So the amplitude can be electrical tension, and it will be defined by the magnetic field. The greater the voltage we apply to our electromagnet in our matrix, the greater the generation will be of electrical voltage in our generator for yours. So let's understand now how it works. Let's think here about a waveform whose measurement of this value of peak here is equivalent to 311 volts. What is the effective voltage of this system? We're simply going to take the peak voltage, multiply it by 70.77. This will give us 220 volts. So what do we see when we measure voltage? In a household electrical outlet it is 220 volts. It is the effective voltage. We do not measure peak voltage. We measure the effectiveness of the voltage that will actually gives a quadratic mean of our system. So let's take a look here at the power transfer effects. Let's imagine here that our turbine, which is driving our generator and our turbine, it is receiving a thermal power of the steam that is entering, being admitted in the turbine of 118.7 megacalories per hour. This thermal power that the turbine is receiving, we are imagining a completely hypothetical turbine, where this capacity to receive this thermal power, can it fully deliver this thermal power to the shaft of my generator? So I'm going to deliver it here to the generator shaft, okay. Then I will have the work delivered in power. Sorry, The power delivered in mechanical power is 185 horsepower and this is 135 horsepower. We are admitting that this generator of ours is a ideal generator, which has no losses and our loads are, because it actually uses 3 sets of coils. Phase 2, phase 3, phase. This set of coils phase 2. This other set of phase 3 coils. This set of coils is our generator. As we already know, it has an acting rating, that is, it is equipped with an electromagnet that it is possible to modulate the magnetic field through a current system. Continuous. We have there the power supply of our electric field and the 3 coil sets and providing 3 phases in our generator. So the generator can also be connected in another way. A formula that now appears a third, where the 4th conductor, which we call neutral, and we will soon understand what this neutral is. But let's understand the first phase 1. So, I have a connection here with this coil, okay? And with this other coil and the 2 coils are interconnected. Now through this connection here the output of a coil connects on the other coil and allowing me to do a potential difference called phase 1 or R. Phase 2. It interconnects this second coil that we already saw with the 3rd coil. And in turn it is also connected to the same connection as the others. The other 2 angle pass coils between one set of coils and another of 120 degrees. And this is very important, because when we look at the generation, we either understand or we don't. Let's imagine that this graph here, the amplitude is the voltage, that is, chain voltage, for example, in kilowatts. Let's look here at the R phase. When to do it begins its generation in the T phase. It is already at the end of a decrease from the peak, and while the phase is reaching its value minimum, the minimum possible tension. So while the R phase is 0, the T phase is leaving the maximum, and the S phase has the minimum value. And why? Because there is a time lag between each of the phases of the R phase, of the C phase and the T phase by 120 degrees. Each of these phases here are 120 degrees out of phase with each other. That's where it's going to get you. How we managed to measure the voltage as well. Between the media, we already saw in the other class the effective value of a voltage, but now a voltage. How is the voltage measurement? That we know that as we have already seen the differences, the difference in potential will not be established between two coil sets, either here, or between this and that, between R and T, or between RS, or between the T, as I won't be able to tell you which one it is. The voltage value that I am generating when I place the test lead. My voltage meter, my TP is the TP, is a voltage transducer widely used in generators, that you always put it on the bus to be able to measure the tension that exists between each of the 2 phases. The electrical energy in it transforming into movement, into work. But what happens in this engine? I will have a chain dedicated to magnetizing magnets, that is, I will need a chain so that it stays at the same time, only producing the field and magnetic field. Okay. And I'm going to have a chain that she'll always go to be used for work consumption. I'm gonna have a chain to produce a magnetic field and a current to produce work. There are 2 currents. So the sum of these 2 currents is the total current that the motor needs. Then the engine. There will be 2 currents for circulation. One current that produces the magnetic field, and a current that will produce the work to produce the movement. Okay. So the magnetic field will produce work on the rotor, but I need a current to produce the magnetic field, which is then this. This is the difference factor in an asynchronous motor. The cage rotor needs 2 types of current, a current just to generate the magnetic field and a current to produce the work. We will notice this here. Yes, we have our attention here. Starting at the highest point on our graph, the initial current. It is null at this point, but as it that you will decrease the tension. He increases the current, he increases the current. It will be 1 a.m. that they are, or they will be exactly out of date. Just look at how much tension there will be when the current is 0. Here is maximum this, because this, in this case, is talking about a sinusoidal function. So that effect that we verified with the coil, it will produce this second effect in a sine wave form. When I have maximum voltage in my electrical circuit, I will have the minimum current production and vice versa. When I have maximum current production, minimum attention, or zero tension, the minimum tension would be the excuse here. The minimum tension would be here is where I would have to. The value, zero current, value of zero current would be this point here. Let's take a good look. So if we superimpose the two graphs, we will see that there is a time lag. There is a phase shift between the voltage and current in the current voltage, exact 90 degrees to a coil, a resistance-free coil, mica. I thought if something is equal to 0, okay, this lag will be 90 degrees. If we put our oscilloscope on, that's when things get complicated, right? Because we can now see here the behavior of the two currents. The current used to produce work in the motor, it is synchronized with the voltage. And the current that is used to produce the magnetic field, it is out of phase by 90 degrees. So the current here has the voltage and current in blue on the oscilloscope. They are they are synchronized in phase. There is no undoing of these currents. So the electrical trigon diagram will be presented as follows. Active power as the adjacent leg to reactive power, never having an opposite. And our apparent power on the hypotenuse. Okay, reactive that does not exist is apparent. What is the value of apparent power in this case? If we don't have the value of the reactive power, it doesn't exist, it's null. What happens if it is null? It will tend to 0. So the three of us, he goes down, 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 until apparent power equals active power. So when the angle is 0, the power is active, will be exactly the same as the apparent power. There is no lag, there is no angle, there is no angle, there is no hypotenuse. It fits perfectly on the opposite leg. Therefore, the apparent power is equal. The active power is 69 kilowatts, which is equivalent to 69 kilovolts. So if I buy a 69 kilograms generator and I turn on that generator to a resistance bank, which will consume 69 kilowatts, it is exactly the same thing. It will be applied. It is equivalent to active power, okay. As an example in the information here, quite a few interesting things about a plate and a plate of one of these electric motors for you that can verify. There will always be a plate on the engine casing indicating a series of information about this engine. So let's see the main information here now. The first line he indicates is a 3-phase motor. So this here is the symbol of a 3-phase motor. This here is the engine model. The power delivered in kilowatts or horsepower in HP. Here it is indicating here that it is 7.5 kilowatts or 10 horsepower. The rotation is 1,760 revolutions per minute. So the engine runs at 1 rotation. Since it is asynchronous, I have already mentioned that a motor runs with 4 poles. This is already indicating to us that he is 4 points, and these poles will be here below, here and here in. The manufacturer indicates how you should connect these poles. So the system.
Então, até mais. Tchau, tchau.